the screen?
Yes, sir.
Good.
Sir,
So,
in the key
yeah,
is given, there is a correction.
sorry.
In the solutions updated for the quiz 2,
Yes.
answer for the question contain language that does not contain substring 00. The answer given is not satisfying, sir.
Uh, Please send me a message on Teams, okay? And I'll look at it. Okay?
Yes, I have posted it in the general, sir.
Yes, yes. Okay, good. Uh, so, yeah. So we are looking at the pumping lemma. Right? And I'll write it in a much more concise form. And you have to remember this lemma. You have to learn it by heart. Because this is one of the most important theorems for regular languages. The other theorem is the Myhill-Nerode theorem, which we'll see a little later. And of course, we have already seen Kleene theorem. If L is regular, then there is a constant n, which of course depends on L. We don't write that such that for all W belonging to L with the length of W being greater than equal n, there exists three strings X, Y, and Z. These belong to sigma star, of course, such that one, W equals X, Y, Z. Two, Y not equals epsilon. Three, the length of XY is less than equal n. Four, for all k greater than equal 0, x, y to the k, z belongs to L. So please commit to memory the entire thing. It should not be too difficult. Any doubts about the statement of the lemma? Any doubts? Okay, the first thing to note is this lemma is actually an implication. If L is regular, this is of course for all L, which is implicit here. So if L is regular, then something is true, right? It doesn't say if and only if, okay? So if for a language L, there is a constant n satisfying all these, it doesn't mean that L has to be regular. Please understand this. That's the first thing to understand. It says A implies B, okay? It doesn't say A if and only if B, okay? And indeed, there are languages which are not regular, which also satisfy these conditions. Okay, there are examples to show that. Therefore, uh, the pumping lemma is not useful in proving that a language is regular. It is only useful in proving that it is not regular, right? That's the first thing to know. Okay, uh, let us prove it. And I'll only give an informal proof. I'll leave the formalization to you. I mean, we have a severe lack of time because of these quizzes. They are eating into our classes. So, and at the same time, I don't want to have quizzes on holidays, Saturdays, Sundays, right? So we'll have to skip on some of the details, especially the formal part. But this will convey the idea, right? So if, sorry, suppose M is a DFA. Suppose L is regular. And so we know that there exists a DFA which accepts L. And M is a DFA. With N states that accepts L. Right? Then we choose a string W. Sorry, I shouldn't say it, we choose. So let W be any string. The statement of the lemma says for all W, right? So let W be A1, A2, and so on up to AM. With the length of W is M, of course, M greater than equal N. So let us take any string W of length greater than equal to N, where N is the number of states in the DFA M. And consider M's execution or run, let's call it should I call it execution? M's run on W. It is of this form, right? You start in the initial state Q0. Then on reading A1, you go to some state Q1. On reading A2, you go to some state Q2, and so on. At the Qm minus 1, you read AM and go into Qm, right? Now, by the pigeonhole principle, because there are M plus 1 states here in this execution, and the automaton has only N states, we can say that since M is greater than equal N, and there are actually M plus 1 states here, right? There must be 2 states Qi and Qj, where I is not equal to j, from the m+1 states, such that Qi equals Qj. The proof is very simple. So you have a situation like this. You start at Q0. I'm talking about this run or computation or execution. Then after looking at a finite prefix of the string A1 to AM, and that prefix could be empty. So Qi and Qj could be both equal to Q0. That's possible, right? Because I is less, let's suppose, let's say I is strictly less than j. We know that it's not equal, so let's, I mean, without loss of generality, we can say that I is less than j. So once you reach Qi, after um, traversing a few edges, you come back to that same state, and finally you. And these are, maybe I should make it clearer that these are squiggly lines. These are not single transitions. Perhaps that is not clear. This is QM. Right? And yeah, so let's assume that W belongs to L, because that is what the statement of the theorem says. So this is a final state, right? And then there's this, right? So this is the string A, sorry, A1 A1 to AI, and this is the string AI plus 1 to AJ, and this is the string AJ plus 1 to AM, right? And what can you say about what can you, and let's suppose that suppose I is the smallest such index. Okay, so I is the first index where the state Qi occurs again, because many states may repeat. It's not just one state will repeat. There could be many states. We are just considering the first state that repeats, right? Then what can you say about this length of A1 to AI? What can you definitely say about this? What can you say about this? The length of
It
this
is less
string.
than
It is less than equal n. Okay. Why? Because there's no repetition up to I. Up to I, there's no repetition. So if it had more than n states, there would be repetition. But because there is no repetition, it has to be less than equal n. So call this x. Define x well, I'll write it later. Number 2, what can you say about the length of a I plus 1 What can you say about this? All we know is that I is strictly less than j, right? So what can we assert about this string?
that it is not empty.
It is not empty, right? That we can assert. And further, so let x equals a1 to ai, y equals ai plus 1 up to a j, and z, let z be a j plus 1 to a m, right? So we got the first two conditions. Why is it true? Then for all k greater than equals 0, right? X, y to the k, z is also in L. Is that because if you follow x, the string x, you come from q0 to qi, and qi is the same as qj. And you can go any number of times, including 0 times, and come back to the same state. Okay, so if you loop k times, the string you follow is y to the power k, and then just follow the string z to go to the final state. So that gives us all the 4 conditions here. So first of all, we took a w belonging to L, and then by arguing that at least one state will repeat, and let that state be the earliest one in the computation of m on w, And then we showed that there indeed exist these strings x, y, z, which satisfied these conditions. Right. So, any doubts about this? Any doubts about the proof? It is informal.
Sir,
Yes.
that length of x is less than or equal to n, but in the third point it's given length of xy is less than or equal to n.
Oh, I'm sorry. Yes. I'm sorry about that. You're right. Uh, is this less than equal n? Is this less than equal n?
Sir, it is strictly less than n, sir.
No. No. One state is repeated here. Just wait a minute. So we must argue that this is less than equal n, and why is that? Can anyone tell me why this should be less than equal n?
So won't it just be like a tree with one cycle? Because there's only exactly one node repeated. So a tree has at -1 edges plus 1, so it can be at most n.
No. No, that is not the case, because there may be cycles where within.
Sir, I think currently it is okay because like the first one is xy. So as said in the lemma, it should be less than or equal to n only.
Yeah, but why is A1 to AJ? Oh, I see. Yeah. No, that argument was correct. The first state that is repeated. So on this loop, there is no other state which is repeated. That is correct, because this I is the smallest such index, right? So this is less than equal n, because only one state is repeated, right? As you said, as someone just said, only one state is repeated. That's how, because I is the smallest, oops. So that was the correct answer. Only one state is repeated in following this string from A1 to AJ. Only one state is repeated. So at most there'll be n plus 1 states. And if a computation involves n plus 1 states, then the string uh, that is processed is of length n, right? Yeah. So do you follow that?
Yes, sir.
Since at most n plus 1 states are visited when processing the string A1 to AJ, right? Okay, so this is an informal proof because I'm not using delta hat and all that. So all this can be formalized using delta hat, and I leave that to you, and you can read it from the book. Okay,
Hello,
let's
sir.
not go in. Yes.
Sir, here we have said that I is the smallest index such that there is a cycle like this. So
Yes.
can it happen like if j is I plus 4 or something like that, and there is one more index from like I plus 2, which also satisfies this condition. So there may be multiple loops within these loops too, no?
No. It cannot be because at this point, if there is another loop, right,
Yeah.
which finishes before you re-enter QJ,
Mm-hmm.
then it is the earliest index for which there is a loop. Okay, so it cannot be the case that these two dots are the same state. That's not possible. Do you see that? The person who asked the question, do you see that? That these two dots cannot be the same state, because then this dot itself will become the first index at which there is a cycle. Do you see that?
Yeah.
Huh?
Yes.
Okay, good. Any other questions? Any other questions? Okay, so it's not a difficult proof. And once you've seen this, you can reproduce it. I mean, once you get the idea, you can reproduce the proof. There are, of course, these subtleties about number of length of the string that you can argue about. Okay. Now, when you are using this lemma, I often see students doing this. They sort of try to prove it again, saying that, oh, this string is greater than n, therefore it must loop at some point. But that is pointless. You have proved it in proving the lemma. Now just use the lemma, right? That is the point of putting it in a lemma, so that we can use it. We don't have to look at how it is proved. Okay. So that shows a lack of understanding of how mathematics works. I mean, when you prove a result, you just use that result. You don't, again, go into justification of that result, right? So when you are trying to use that lemma, don't say, oh, because this string is greater than the number of states, it'll loop on some. That is all that is not needed. All you just use this lemma. Okay, let's do that. So all of you should know this lemma by heart. Okay. It is one of the most important results for regular languages and one of the most more important results in this course. Yes, and this is especially useful for proving that a language is not regular. Okay. And not at all useful for proving that something is regular, because there are non-regular languages which also satisfy the pumping lemma. Okay, so let's proceed. And I think I gave that example. Last time I wrote N, but it doesn't matter whether I write N or I. Okay. So this is the claim. And this is the template for all such proofs. Okay. So if you want to show something is not regular, you assume that it is regular and prove it by contradiction. Okay. So suppose L is not, sorry, suppose L is regular. This is for the sake of contradiction. Then by the pumping lemma, and I'll just write PL, there is a constant N such that okay, this is not part of the proof. Okay. What you do is this. Consider W this particular string, right? So instead of this, I'll write something else. Let N be the constant in the pumping lemma. Okay, because L is regular, by the pumping lemma, there is some constant N, which may depend on L, of course, satisfying something, 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 right? So let N be that constant in the pumping lemma. Okay, I don't want to write the entire statement of the pumping lemma here. So this is the way to write it. Let N be the constant in the pumping lemma. Okay. Then I take a string whose length is more than n. And the choice of this string is up to me, because the theorem says for all w. The theorem says for all w. Okay. So no matter which w I choose, everything that follows should be true, right? So I can choose the string of length greater than equal n, of course, but I cannot choose x, y, and z. I cannot choose x, y, and z. I can choose w. I cannot choose x, y, and z. And I have to show that for all possible choices of x, y, and z, it is not the case that all four of these statements hold. Therefore, one statement, one of these four statements must fail, must be false. And that is the same as saying that the conjunction of 1, 2, and 3 will imply that 4 is false. Implies that 4 is false. And that's what we are going to do. Okay, we'll take a string w and we'll show of length greater than equal n, and we'll show no matter how you break it up into x, y, and z, satisfying these three constraints, there is no way to satisfy the fourth constraint. So is the strategy clear, or do you have doubts about that? And that will give us a contradiction. Yeah. But note that x, we cannot choose x, y, and z. We have to argue that once I've chosen this string greater than of length greater than equal n, the choice of x, y, and z is not up to me. Okay, so it's like a game between the prover and an adversary. The prover is trying to prove that the language is not regular, and the adversary is trying to sort of foil the prover. So the prover will choose w of length greater than equal n. The adversary may choose any x, y, and z, but they must satisfy conditions 1, 2, and 3. And the prover will show that 4 doesn't hold, which means the prover will just have to show one particular value of k or I, whatever, such that x, y to the kz is not in L. So that is the strategy. So let me complete the proof and ask you whether you have any doubts, right? So then by the pumping lemma, there exist strings x, y, and z such that w equals x, y, z y not equals epsilon Well, in the proof, there is a way to avoid writing all this. You can just say let XYZ with a decomposition of W satisfying the clauses in the pumping lemma, something like that. Instead of writing up all this, right? But I have just spelled it out because you may not remember uh, all these clauses, the 4 clauses, right? So remember, how this string is broken up is not up to us. All we know that there exists such a breakup. So consider any such XYZ, since the string, the length of the string XY less than equal N, right? And remember, W itself is this. So the first N symbols are zeros, and the length of XY is less than equal N. So what can you say about X? X is just a string of zeros, some 0 to the R, and Y is also some string of zeros, say 0 to the S, right? And what is Z? Z may have some zeros at the beginning, followed by N ones, where R and T are greater than 0, greater than equal 0, and S is greater than equal 1. Is it clear or not? Why is S greater than equal 1? Because by the lemma, Y is non-empty, right? Yes? Any questions? But X itself can be empty. There's no restriction on X. Any questions, doubts? Now we have to arrive at a contradiction by showing that there is some k such that x y to the power kz is not in L. And in this case, choosing such a k is extremely easy. In fact, any k, any value of k other than 1 will work. K equals 0 will also work. Do you see that? Why is that? Now, x y to the power 0 z, this is just xz, because y to the power 0 is epsilon, so this is just xz. And x is 0 to the r, and t, z is 0 to the t, and 1n, and this is 0 to the power r plus t, 1n. And this is not in L, since r plus t is strictly less than n. Why?
Because r plus s plus t is n and s is greater than or equal to 1.
Since r plus s plus t equals n and s is greater than equal 1. Okay. R plus s plus t is the number of zeros. Okay. And as I said, you could have chosen any value of k other than 1, and the proof would go through. But obviously, you'd like to choose a value of k which gives a simpler expression, right? Now, in many cases, so where exactly are the what should I say, are the real insights in this proof? One is in the choice. In general, the insight in the proof or creativity or whatever is in the choice of W such that W belongs to L and the length of W is greater than equal N. That's one. Number two, you don't know anything about X, Y, Z. All you can, so you'll be given X, Y, Z satisfying those constraints, right? And then you have to assume that usually that's how it works. You assume that 1, 2, and 3 are true, but 4 is false. I mean, 1, 2, 1, if 1, 2, and 3 are true, then 4 must be false. And because 4 is a universal statement, right? This 4, clause 4, it's a universally quantified statement. So to show that it is false, you have to come up with an I or J or whatever, you can call it K even, such that, so choice of K such that X, Y to the K, Z. So these are the only two things that you need to do. Yeah. And in this particular example, both were easy. But in general, both can be difficult. Okay. And not all proofs are as easy as this, and some may be quite hard. So this is just a warning. So let us take another example. Equal number of zeros and ones. We are working with the binary alphabet. I'm not writing that. So this is not regular. And you may say, oh, but that's what we just showed. No, the language we took was different. The first language was 0 to the I followed by 1 to the I, right? For all I. So that's not the same as this one. I hope you realize that. Because the zeros and ones can occur anywhere, right? So this is not regular either. Can we follow the same strategy? I mean, can we choose the same string that we did there? We can. Do you see that? We can choose the same string W, even though it's a different language, right? And everything will go through. Do you see that? Any doubts? Because by your choice, the string Y will lie within, the string Y will consist of a non-empty string of zeros. And when you pump it 0 number of times, as we did in the first case, the number of zeros will reduce, but the number of ones will remain the same, and therefore that resulting string is not in L, right? So this wasn't difficult either. But if I take a more difficult thing, I will not be able to finish in 2 minutes. But let me write it anyway, and you should try it on your own. And here the alphabet is, you can take the singleton alphabet, just zeros. I is prime. So this will require some more thinking. It is not regular, right? And you can take the alphabet here, either the binary alphabet, it doesn't matter. You can take to be just zeros, so just the unary alphabet, right? So think about it. We'll discuss it in the next class. Yeah. And let me stop there.
Hello, sir.
Yes.
Sir, I had a doubt in the pumping lemma proof. Sir, can you go to that space?
Yes.
So here we have taken I to be the such smallest index such that Qi and Qj are equal. But rather, shouldn't we take J the smallest index such that Qi and Qj are equal? I think we should here mention that suppose J is the smallest such index such that Qi equals to Qj.
You can show that
This is because,
it will be
sir, in this thing,
I'm claiming that I claim that what you are saying and what I am saying are equivalent. And I actually showed you why that is the case. Because but this statement means that from Qi to Qj, Qi is the earliest occurrence of a state which is I mean, you are right in one sense that maybe I need to state it a little more explicitly. This I is the smallest index. Okay, yeah, I get your point. Yeah, let me make it J. That'll remove all ambiguities. Yeah, thanks for pointing that out. So if I so let J be the smallest index at which a state is repeated. Okay. Yes, what you say is right. Yeah, that's the way to state it.
Excuse me, sir.
Yeah.
Sir, it
Yeah.
could also be I. I is the largest such index.
No. You process the string, and as you go along, the moment a state is repeated, the first time it happens, that index is J. Okay. And then there's no confusion. Right. So this should indeed be J. I completely agree. Yeah. There's no confusion here. The first time
Okay.
you see a repetition, the first time, right? You call that index J, right? And of course, there must be some I less than equal J such that QI equals QJ, right? Okay, let's stop there. Thank you for pointing this out.